Here, question number 55, we are going to solve it now. The question is, a point charge is moving with a uniform velocity beta c along the positive is a x direction, parallel to and very close to the corrugated the metal sheet. That means the metal sheet, near the metal sheet, it will follow the wavelength of the point mass. It will be equal to the distance between the two atomic distance. That is the wavelength of the point charge. Here it is given the small capital L represents the distance between the two throw. So that is the wavelength of the electron. Now what they are asking means the wavelength of the electromagnetic radiation received by the observer along the direction of the motion is what is the thing we are going to solve now.
Actually, what they are given here, the point charge moving with a uniform velocity. First we need to write the given quantity. The velocity of the point charge, that would be equal to beta times c along the positive x direction, parallel very close to the corrugated metal. Here actually it is given it is the distance between the and the throw is L, as well as here also it is L. The point charge is moving, this is given like that. It's a beta c towards a positive x-axis. This is a positive x-axis direction. Here the observer is looking the point charge movement. That means it is moving towards the observer. This is a metal sheet. This variation in the surface of the metal sheet, it is given like that. So you can conclude one thing, the wavelength of the point charge, it is equal to L, because the wavelength you can define, it's a distance between the any crest to crest or toe to toe. So the wavelength of the point charge, that should be equal to L, the point charge wavelength. That is the first observation we can make it here. So the point charge wavelength is equal to L. The next quantity what we want to do means we want to find the wavelength of the electromagnetic radiation received by the observer from the Doppler shift. Suppose you can do the wavelength of the original wavelength of the point charge, that would be equal to, you can call it a lambda naught, that would be equal to L. From the Doppler effect, the relation between the moving charge towards the observer, the wavelength, observed wavelength is equal to, you can call it observed wavelength is equal to the original wavelength times 1 minus beta prime divided by 1 plus beta prime. Here, because here velocity of the point charge, it is given beta times c, that's why I am making different symbol here. Beta prime is nothing but it's a velocity of the point charge divided by the c. That is the relation we can derive it from the Doppler shift. So this is actually the observed wavelength according to the Doppler shift with respect to the original wavelength. Now what we are going to do, the lambda observed, that would be equal to lambda naught square root of 1 minus beta prime 1 plus beta prime. We are going to multiply the numerator denominator by 1 plus beta prime by 1 plus beta prime. Now what we are getting after the multiplication, it would be equal to lambda naught, the numerator it will be turned out to a plus b into a minus b, it will be 1 a square minus b square 1 minus beta prime square divided by 1 plus beta, because 1 plus beta prime 1 plus beta prime, it is square. If you are cancelling the square root, it will give 1 plus beta. We know the what is a lambda naught, it is defined from the metal sheet. We can define the metal surface, we can define it is L, the length. There is a lambda naught, that would be equal to, we know the what is the beta prime. Beta prime is nothing but we can define 1 plus it's v prime by c. square root of 1 minus beta prime square. So this is the expression we have. Now what we want to do, the lambda observed wavelength, that should be equal to L by 1 plus, we know what is a V prime. V prime means the velocity of the point charge, the moving point charge, that is, it's actually, it is here. If you look at the velocity of the moving point charge, that is equal to beta c divided by the c square root of 1 minus beta prime square. Look at this expression. It's 1 plus v prime by c. V prime is nothing but it's the point charge velocity moving along the positive x direction. It is beta times c. That's why we have written here. Everything is remaining same. So the lambda observed wavelength by the observer, that should be equal to L. You can cancel this one 1 plus beta square root of 1 minus beta prime square. In charge, it will move equal to the velocity of the light. Suppose approximately beta value you can take 0.9 or something 0.8, something like that. In general, the velocity, it is equal to the velocity of the light. That's why the velocity of the point charge, you can write it's a beta times c, it's given. That means the beta factor, it may be approximately, you can put it's a 0.7 to 0.9. It's a lot of experimental observation source, it's nearly equal to the velocity of the light. That means 0.9 c or 0.7 c. So the 1 plus beta, you can write it's a 1 plus 0.9 or approximately equal to the beta value, it's a fraction quantity, it's a zero point 0.9 or 0.8 or 0.6. It's approximately equal to 1, or you can write it's approximately equal to beta. If it is because it's around, it's not much greater than 1, or it is not much less than 1, it is approximately around the 1. So either you can write it's 1 or beta. Then the final lambda observed wavelength L divided by the beta, that should be equal to 1 minus the beta prime square. In general, the beta is equal to the beta prime, because both of them are can be represented by, it's a v by c only, the velocity of the particle compared with the velocity of the light. That is we can define by beta. So the lambda observed wavelength, you can write in general, it will be equal to lambda by beta 1 minus beta square.
From the above calculation, we got the answer L by beta square root of 1 by beta square. So this is the right answer.